So I'm probably going to get started. My name's Mike Sherman. I'm the infrastructure lead for Chameleon. This particular tutorial is about what and why and how to use the edge devices in Chameleon. So, how is it different from all of the servers and bare metal usage and virtual machines that we've been talking about earlier today, and in the earlier tutorials and in all the other talks yesterday? And, what's the point? What can you do with it? And then I've got a bunch of worked examples, but we've got a fairly long slot, although Paul can at some point, if you need more time, we may cut this short if we run out of questions, so we can play this by ear a little bit. But what I mean to say is that I'd really like this to be a bit interactive. I'd like to get questions from people, talk about well, here's what we do now, here's what we could do, here's how it's worked out, because Edge is the newest part of the system, and it's the part that's changing the most, and that we're most able to extend to add features and support new use cases. We've got some kind of intro slides to set the context here. It's mostly that one of Chameleon's goals is to have a really wide variety of hardware in a wide variety of contexts, so that you can run this wide range of experiments, support more users, and especially try to support experiments that need to cross traditional boundaries. So instead of everything's in the data center or something that's at the edge only, which you could do if you just had a Pi on your desk, well, what can we do if we have both of them in Chameleon and they have the same reservation mechanisms and they can all access the shared storage and you can orchestrate across them? And especially with inference being popular now, that's started really driving some interest in this. And, do I gather data on the edge and upload it to the cloud? Do I gather data on the edge and process it locally with a model I trained on the cloud? Do I do the inference remotely? How do I know when to make that trade-off, or what is a good trade-off? How does this depend on what hardware I have, what power constraints I have? And so it's, I think it's an exciting area. We've showed this hardware slide before. This is just kind of showing how does it fit into the larger context. Each of these blue boxes here are different sites, and what this mostly means is that it's a group of hardware that has relatively good connectivity between it, and you can reference and configure it sort of as a unit. You want 5 nodes at UC, you want 6 nodes at TAC. It's a little bit harder to do 3 nodes at UC and 3 nodes at TAC because you've got 2 different control planes. And then the green line here is connectivity over the public internet via public IPs. And so Chi at UC and Chi at TAC at a high level mostly just have public connectivity to the internet, and then you can do whatever you want on top of that. Chi at Edge works the same way, where it's not directly connected to any of the site's internal networks, but you can send traffic from any of the edge devices over the public internet to any of the other sites. And we also provide some mechanisms to be able to connect into these devices. This is our usual experimental workflow, which again, I've got here for reference. You can find the slides. And so I'm going to be talking about in Chi at Edge in particular, how do you discover resources? What do we have? How do you actually allocate them? How do you configure things once you've allocated it? And then run your experiment and actually get the data out and analyze your results. We've got a bunch of cool projects that have used Chi at Edge already. Some of them have done federated learning. Some of them have been doing biometrics at the edge. We've done network traffic fingerprinting using the edge devices to sort of sniff network traffic and characterize it. And the goal for a lot of these has been to do the reservation and orchestration and analysis from a single Jupyter notebook in our Jupyter environment. Some of the big differences to make this work is our deep reconfiguration on bare metal nodes and VMs relies on a lot of hardware and tooling. So the VMs have hypervisors, we've got private networks between them. The bare metal nodes have out-of-band management, and we can customize the networks they attach to. And the question is, how do we give you this kind of low-level access that you want to actually do interesting things and also not break this thing? Because on here, we don't have out-of-band management, we don't have a hypervisor, we don't have a lot of resource headroom. And so we are deploying, or we're letting you deploy containers onto these devices, primarily so you can't do things like delete the boot partition, or otherwise render the device not usable, which is surprisingly easy to do by accident when you're just tinkering with things. As I've been developing this and sometimes running without the guardrails, we found this out the hard way. But to do these interesting things, you still want to access peripherals, sensors and actuators and cameras, and you want to run things like strace or ping and things that might require certain elevated permissions to perform the system's calls. And it's also not super useful if we have all these special edge devices, but they're not at the edge, or they're not at the edge you care about. And so one of the core design portions of Chia Edge was this sort of self-service device enrollment. And so you can take the Raspberry Pi that's been on your desk, and with a couple tools I'll show in a bit, just register it in Chia Edge, bake a SD card image, flash it on, and it will pop online, self-enroll in Chia Edge, and you can start using it. And you can also let other people use it remotely. If you want to learn more about how this actually works and how it was implemented, we've got a paper in PERC 2025, which has a lot of the technical details. Sort of a bulleted list of capabilities. I'm not going to go through all of them. It uses the same identity federation as the rest of Chameleon. You do get the ability to attach public IPs to these. It's not always the right answer, but it's something you can do. We've got a whole bunch of different devices, and importantly, because of the reservations, you're still reserving time slots on devices. During that time slot, you can launch as many containers as you want. There's no limit on one container at a time. So that's a big difference from bare metal and KVM, where you're sort of working on single instances. If you want, you can launch, a camera 1 container and a camera 2 container and do something to have them talk to each other. The reservation just keeps someone else from launching containers on there and make sure that things are cleaned up between users. Just got a couple other examples of cool things people have done. So one of them we had was using Jetson Nano to detect fish and basically do river health measurement by counting how many of what type of fish were present. And we've also got actually Rick Anderson, if you run into him, was mentoring some students for this. This was doing some end-to-end autonomous, end-to-end trained autonomous self-driving cars driven by a Raspberry Pi, and the whole thing orchestrated through Chia Edge. So you'd use this to first deploy a sort of data collection container, drive it around with a remote controller, upload the data to the cloud, train a model, download the model back down, and then see how well it did. And it worked surprisingly well, is what I would say. It's pretty easy to train it to drive uniformly badly. This did raise a lot of challenges, especially for sort of user interaction, and this has shaped how we've been designing the interfaces going forwards. Common issues are if you plug this into Ethernet, that's easy because it just plugs in and works. If you want to get it on wireless, you need to get the credentials on there. And it's hard to find out if it worked because you generally don't have insight into your campus Wi-Fi. And if it didn't come online, mostly you find out that, well, it's not working and I don't know why yet. And so there's some things we're working on to try to make this feedback loop shorter and show you more clearly did this work or not. We've got some experiment patterns for like how should you upload data to the object store or to other types of storage, and how can you reserve a node to train on. The KVM GPU nodes we have now are really good for this, especially if you only need a part of a GPU, if the models aren't very big. And we've also got some examples that Rick's been contributing about different ways to get local access to it so that you don't need to worry about the latency from here to the cloud for parts of your experiment. Quick run through of what we have. This is just a list of things, but we've got some increasing amounts of documentation that will have links in the next slide if you need. So we've got a sort of auto-discovered list of here's everything that's online right now and what it is and what project owns it and does it have peripherals attached. And our docs go into what are each of these things and link to the sort of manufacturer's specs and what are the peripherals and what is the actual hardware in here, and also how do you access it with these device profiles to map it into your container, and various photos and other things. And this is not complete because people have added a whole bunch of different types of stuff to GeoEdge. And so right now what we've documented is the core part of like stuff that we added, we know all the details of. And so one of the things I'll be asking for some feedback on as we go through is what kinds of things would you want to add to GeoEdge? And are these easy or hard, and how would you find the right info, and how do you know if it's working right or not, and kind of all of these different details. So you can find all of the links here in the slides that are shared on the website. What I'm going to run through first is I've got 3 worked examples, which are all grabbing different devices that are out in our cloud right now, and grabbing data from the sensors. And let's see if I can get Zoom to switch what I'm sharing real quick. It looks like I can. That's amazing. At some point I stopped trusting technology. Right, so one of the things I will show off is in our the Gitbook documentation page that was linked. This is kind of our landing page for where to find everything else. This is linking to the OpenStack dashboard for GeoEdge, which looks like the others, but we'll just show you containers instead of other instances. It's linking to our library of examples in Trovy, and this will be extended as we add more supported things. And you can also search for these examples there, and all of the source for all of them is up on GitHub, including the recipes for building and customizing the container images. And let's see, so the first one I've got here is just grabbing a camera, and if I can get Zoom's menu bar out of the way, that would be great. So the first one here is this camera tutorial. And this is going to run through how do you pick a device, how do you reserve it, and all of this. So this first widget is the same workflow as the rest of Chameleon. It's authenticate to the site and select a project. I'm using Chameleon. If you've gone through the various tutorial sign-up links, you can use that one and you'll have access. We make a lease for it. This extra stuff here is just because I know that the devices that start with the string IoT RPi4 PyCam have the PyCamera attached, which we got from the device browser. And this is something where we're going to be improving the ergonomics here so that you don't have to do as much cross-referencing and you can ask it directly in this query interface. And so this is going to be telling us, which things are available. Right now it says nothing's available, and that's because I've got something left over from my last dry run of this, and so we will just delete that out of here. And now if I rerun this, this should show up as available. Yep. So as there's still a bit of jumping between interfaces, and we've got a list of places where you shouldn't have to do that. So now we know what this is named, and so we can make a lease. I've picked a few hours here so that it just cleans up after itself pretty quickly. And we'll just wait for that to start up. And you only have to do this this once, and then everything else you can rerun within your lease and just keep reconfiguring it. It generally takes a few seconds to start up. Now to actually access the stuff in here, this Docker image, the Docker file to build this image is in this artifact as well and in this repo. This just contains the Raspberry Pi libcamera drivers and utilities precompiled so that you don't have to go track them down. It's one of the things that gets prepackaged in Raspberry Pi's official Raspbian images and is available in some of the apt repos. But because it's kind of sensitive to, oh, what kernel are you running, and when you're running this in a container, it's sometimes frustrating to find the right drivers. And so for each of these peripherals, we try to provide here's a known good way to get the working drivers, and you don't have to worry about it. But you can always build your own Docker image, either following this example or just using it as a base image. They're deliberately pretty minimal. And so what I'm doing here is I'm going to launch this container using this reservation. I'm telling it to sleep forever instead of running a command so that the container doesn't exit. This is another big difference between the sort of container and the instance workflow is by default containers, they really want us to use stateless containers, and we really don't want to. And so we're always railing against the cloud nativeness of the world here. So we're telling this here to just run a shell and sleep forever, and we're gonna run all of our other commands interactively. What you could do here, though, if you have a more complex program and you want it to continue running, say you've got something that's a Python loop and it's going to be checking for data and uploading it, it should run for a long time, it would be a good practice to put that as the command or entry point here so that if your program crashes, the container exits and you find out. So there's this kind of interactive versus non-interactive workflow there. The last part are the device profiles I mentioned. These are all listed in the documentation page for the peripherals. And what these do is these just map items from /dev whatever from the host into the container. And so for the Raspberry Pi camera, for a variety of reasons, it makes 27 different device nodes to expose every different video accelerator feature as a different device, and that's very painful to pass through by hand. And so this Pi lib camera device profile passes through almost all of them, and then the Pi camera 3 profile here is the extra 2 that show up if you're using the newer cameras with autofocus. So this is a lot of talking and not a lot of doing, but it's important because if you leave something out, you will just get a message about, couldn't map this device profile, or you'll get these inexplicable, I couldn't find a camera messages. And so we've got some examples later about how to actually debug that. But here we are running this just upstream raspbicam hello command to just enumerate all the found cameras and their settings. And if you don't have the device profiles right, or if you're on the wrong device, or if the camera is not present, this command will just say, found no cameras. So it's a good sanity check. The other part that is different from most of the rest of Chameleon is a lot of our examples here are, let's do these sort of interactive workflows, but driven from the notebook. Because you can choose to go back to Horizon and go to containers and go to your container and go to the console and look around in your console, and this is not a very good console, and it also won't give you a sort of a record of what you've done. And so this can be useful for some quick sanity checks, but I'll show you some better ways to get this kind of direct interactive use later. And so for these examples, we're instead going to tell it, run a command and tell me the result. Here's just, we're just printing std out. This is actually more nicely formatted than it would be in that web console because it's got a better shell. And we can also see that it saved the file we asked for, and we can ask it to copy that image from the device up to our notebook and then just show it in the notebook. And so this is a trivial example, and it looks like my camera tipped over, so it's no longer pointed quite as nicely at the Chameleon logo sign I had it pointed at. Been meaning to get like one of those drinking birds or something to get like nice motion for video or motion detection. And we also just have an example here of, instead of just running a command one at a time, you can also use the libraries. We've got this really hello world camera Python script here that is just how to use the PyCamera 2 libraries, which use this libcamera driver. And it does exactly the same thing we just did with the command line. And so all we're doing here is we're just copying the our little Python script up and then executing it. And this is one way to have a reasonably fast development loop. Edit code locally, upload and execute, but not lose your data if something hiccups in the edge device. And so it's run the same stuff, and we're copying the same image back, and we see we get the same results except it's blurry because this missed some default for dealing with the autofocus. You can also do the same thing, executing a command to capture video. The one limitation here is right now this command.execute has a relatively short timeout. You may have heard some people yesterday talking about, how did I know if things were working? The command sort of stopped in the middle. Right now, that's a limitation of how we're executing these commands over some WebSockets, and there's some fixing we can do there. But instead, in the meantime, I'd recommend there are things you can do to execute this in the background, or otherwise have ways to sort of set up a long-running process and get the check on it periodically instead of needing your Jupyter session to stay alive the whole time. And the main issue here is the Raspberry Pi 4s. They can save this H.264 or MP4 data, but they don't have hardware encoding for a format your browser likes. And so I can't just easily show you, here's the video we recorded in the notebooks. So you'll have to run something offline to convert this H.264 to something useful. The other device types, the Pi 5s and the Jetsons, do have hardware encoding, and so you can actually ask it, please save this in a format I can read on my web browser. And then we just finish with these kind of cleanup things here, just referencing your container and lease. They will time out at the end of the lease automatically and clean up, but because we're about to reuse the same device for something else, this makes sure we don't step on ourselves. And you can always go back over to the Horizon dashboard and just see, do I have anything running here? The next one is, actually before I move on to this next one, I should ask if there's any questions or comments on this. Okay, so the next one is we've got a variety of sense hats and sensors. The Raspberry Pi Sense hat here I'm going to run through. It's the same one we've got on here. And so it's got this LED display you can make pretty pictures on. It's got some 9-axis IMU on there, so it's magnetometer, accelerometer, and gyroscope for all the different kinds of orientation. It's got pressure, temperature, humidity, and so on. And you can use these either through the kind of high-level libraries that Raspberry Pi provides for this, or you can choose to go low-level and just access it directly over the I2C bus, because they're all very standard sensors that you can go look up the data sheets for. And this is meant to be an example of, if you plug in something that would work on any normal Pi, you can almost certainly make it work in Chia Edge, because you can map the same interfaces that you can map the GPIO, the I2C, SPI, whatever, and send the same commands to the same peripheral. There's just a little bit more wrapping so you don't brick it. or so I don't break it. Same thing. We're actually reserving the same device here just because I've got one device sitting on my desk back at UChicago that has the Sense Hat and the camera, which in hindsight was maybe poor planning for a tutorial. But that's how we do things sometimes. Making the same lease in the same way. And then we've got just same concept. We've got this Sense Hat image here that has the drivers and binaries for both this Raspberry Pi Sense Hat and also has the drivers and binaries for a common Sense Hat that WaveShare provides. And this Docker file is a little bit longer and more involved. This is just to minimize the final output size. You can just naively apt install and pip install everything. This just makes it a bit smaller and faster to download. To sort of build all the wheels once and then copy them into a runtime image that doesn't have all the build dependencies. But if you're just using the image, you don't need to worry about that. This is using the Pi Sense Hat device profile, which mostly just maps the GPIO and I2C devices into the container. And our documentation page does list for each of these hats, what are all of the sensors, what I2C addresses do they listen at, how do you interact with them, where do you find more documentation. And this also shows a few other ways to do this kind of iterative development. And so this is, this is kind of hacky, but for simple examples, you can just send Python code over as a string if you don't want to deal with copying a file back and forth. But this is telling us we can at least see the sensors and our dependencies are present, we're using the right image. And this is just this library exists and we're using the hello world in the library. But we can also poke around at a lower level and run commands like I2C detect, from which interface and which things are currently registered in the device. And what I'm going to switch to next is this has all been driven from the notebook, and this is useful if you mostly know what you want to do. You're pretty sure you know what the dependencies you need are, you're pretty sure what the interfaces are, and so this becomes a nice way to do kind of literate programming and do something that's shareable and reproducible. But especially when you're starting out, you often don't know this, and so what we can do instead is set up an interactive development environment of different sorts. And the kind of brute force way to do this is run a container with SSH in it. And then do whatever you want. And that bypasses anything that has to do with Jupyter if it ends up being a impediment. And so we can, same as before, run through the authentication. Here, we're not checking for any particular hardware, so this is just going to tell us, there's a whole bunch of Pis, we're going to pick one. I'm going to give it some random name here and pick a 24-hour release so that it doesn't suddenly delete my container if I've been changing things in there. And this is just picking, what's the first device on the list? We can always pick more specifically, but for this example, I don't actually care. And this example here, I'm going to use my image with SSH in it. This is just Ubuntu plus SSH plus a couple very minor hacks to make PAM and login things not yell at you when you're running SSH in this really minimal container environment. But there's a lot of ways you could do this. You could also choose to, instead of SSH, you might want to put VS Code in a container or put some other ID in a container, or whatever you want to expose and connect to over a public IP. If you can run it in a container, you can do this. And so you're also free to use this as an example to base off of to build whatever the thing you need is. So our container is running. Because we want this to be long running, we've got SSHD running as the entry point. And To do this the stupid simple way, we're just going to copy a file over that has the SSH public key we want to allow, which I'm going to copy and paste here and hopefully not show. Oh, perfect, it's not on the shared screen. So I am just going to copy and paste the public key that I'm not going to fat finger and be the private key. I really like the EDE 25519 keys just because they're short and easy to paste. And so I've just edited this file in place, and we're going to upload that file. Maybe. Is it not happy? Well, this is a problem, but it's also a learning experience for everyone. So we are going to try launching the container again to see what happened. It's possible that just what happened is SSH crashed for some reason.
You never ran the.
Oh yeah, that's also very possible that it was just state left behind there.
Yeah.
See, this is why pair programming is important. So it took a bit longer to pull that Docker image. Sometimes there's fairly long pauses just because the Pis are on these SD card storage, and they also have fairly teeny processors, and one of the things that's actually a pretty heavy load for them is downloading and decompressing a compressed Docker image. And so that will actually peg the CPU on the Pi for a while. The Pi 5s and the Jetsons are significantly faster at this just because they're not CPU bound. And some of the Jetsons have actually really nice fast NVMe storage, and we'll just do this in a flash. And now this will actually execute. There we go. Upload, and we're copying, setting the right permissions and catting it in there, and telling us what's in the correct file. We've done it this kind of roundabout way because often the system will be like, no, you can't copy over this file that's owned by root, and this just sidesteps some permission issues that we have probably fixed, but it's a little belt and suspenders. And now all we can do, and we ignore these warning messages about using a old version of the library here, is we've attached a public IP address to this edge device. And this edge device is at UChicago, but the public IP address is in Texas. And this is because all of the devices have a WireGuard, I was going to call it a mesh network, but it's more of a hub and spoke network, linking them all to an overlay. And that core server is in Texas at TAC. And so the floating IPs are in TAC's IP address space. The consequence of this is that we're going to connect to this, but our connection is going to go from here to Texas to Chicago and then back. And so there are better ways to do this, but importantly, this makes all of the traffic go through IP address space that we control, and no one will get angry if users do things. But I've got this address, and I should be able to just SSH directly as this. And let's, is there a way I can, at some point I should learn if there's a hotkey to change which screen I'm sharing. And so we're just going to SSH to that, and we now have a session inside our container on this edge device. And we can see that because we haven't mapped anything in, /dev is very, very empty and only has the things that the system really needs. But we are free to do a apt-get update, install things, modify files, do whatever. The caveat being that if your container is deleted, you lose all the changes in here. This is all ephemeral. One of the things on our roadmap is adding some persistent local storage on the device that's cleaned up when your lease ends instead of when your container exits. And one bit of feedback that would be super helpful is when you're doing interactive development, what paths should be preserved? It turns out it's relatively difficult in Kubernetes land to make like the root actually be persistent, but it's very easy to make a /workdir or something. But because everyone has different workflows, we'd want to avoid, oh, we preserved half of this stuff, but not what you were expecting. And so we can, apps get install MTR or a trace route or a benchmark or whatever it is we want. Generally, we recommend, because this installation process is pretty slow and ephemeral, it's much better if possible to bake it into the source image you're using. Any heavy dependencies and any big source files, throw them all in your Docker image, upload it to Docker Hub, and then launch from that, so that you've got a smaller delta here. And so you can see this is coming out, this traffic is actually coming out from UChicago. This is coming out from, this is an internal network we have in our IoT lab there, going out through various NAT, going out through peering, and coming out to, to Google. I was actually a little bit inaccurate when I said that all the traffic is going through the tunnel. The traffic we're connecting over is going through the tunnel, but if you're directly sending outbound traffic from the Pi, that's using the local gateway on the device. And that means that things like installing packages or pulling images or related things can be pretty fast. We do have some methods where, for people who contribute a device, you can whitelist or blacklist where the device is allowed to send traffic. So you can say, you're not allowed to scan my home network for printers. Since a lot of people are like, we're just going to put this, in our lab network. We're going to plug it into this. We don't have a sandbox. I'm like, well, let's just make it easy to not shoot yourself in the foot. It also means that one of the things you can just choose to put in a container and use is something like Tailscale or some other, bring your own VPN. Anything that can do NAT hole punching and runs in user space, you can just shove in one of these containers and connect to it locally. And that will bypass the whole hairpin through overlay network to tech system back. And I actually keep mentioning Rick. He gave me a whole bunch of great examples about using Tailscale and using some things with like Python and like gRPC, and just set up like interactive control for your experiment and drive it from your phone or something. I can actually switch back over. So the last thing I had to run through is, how does the actually the bring your own device flow work? I see that I've got, is this gonna go? So the bring your own device flow is, again, it's documented on that same docs page. We have a little command line tool. You can just pip install Python gedge. And it will give you an interface to enroll devices, see what devices you have, customize the downloaded disk images so that they can self-enroll. We have actually some pretty verbose instructions, because Python packaging is often a nightmare. Tried to make this very straightforward, but what you'll need to do to make all this work is, you can go to the g.edge site here, and you can, it's actually the same as all the other sites. To authenticate the client, you'll want to grab either a clouds.yaml or OpenRC file to authenticate as yourself. And what this Edge tool does is it will set up a credential for each device you enroll. So let me switch over to the black screen everyone can watch together with me. So I have a clouds.yaml file, and this just has an entry for each site. And what this lets me do is things like, I just have a site named Edge in that file, and I can just pass that variable in and say, what are all the devices I've enrolled? Because I've been doing most of this, a big chunk of the devices are under my user. But if you or your project enroll a bunch of devices, here's where you'll see the ones you own. They all have a time of last check-in, time they were registered, UUID, and like a human readable name. And we can look at the configured defaults for one of them, such as the one we just looked at. And the way this works here is each device has a credential pair that gets auto-created for it. And that's used for it to tell our system, hey, I have this IP address now, here's my end of the tunnel credentials, and it's how it does the self-enrollment. And this is also how you can update and apply settings. And so this is where you're able to, you could rotate that credential if you wanted. You can say which Chameleon projects are allowed to use this. Say if you wanted to share this with a collaborator or a classroom, and you can tell it, should it be allowed to scan your local network or not? When you go to register a device, what you're doing is you're putting in, telling it just what kind of device is it and who to email if something's happening about it. So if we get an abuse report or if the device goes offline, just who to email. You can customize these app credentials if you want to. It was relatively recently that we added the we'll just set up a pair for you feature. So I'll just register and I'll just pick a Raspberry Pi 4, 64-bit, and so I've just submitted this registration request, and now the system's going to go out and sort of phone home to all these back-end services and register it in the cluster and set up the tunnel. And yep.
Are those the only machines that are kind of supported right now, or can you do other things?
So the ones in this list are the ones that are supported right now. It's not that difficult to add more. There's just a bunch of details, and we've got some docs on our site about what is required to add more devices and add more peripherals. A bunch of this is currently locked behind, well, an admin has to edit a file, but on our roadmap is, how do we model this so that it can be more self-service? One of the big issues is the base OS images available for the Pis and especially the Jetsons. They're often missing kernel modules we need. And so they'll be like, oh, we're going to compile WireGuard from source against this kernel so that it'll work. Or we're going to compile in the missing IP encapsulation kernel module, which NVIDIA didn't bother to include. And so there's a long tail of make X, Y, and Z work so it actually works end to end. But otherwise, the machinery of this doesn't change. Okay, and now I can just see how far this has gotten. And so this has gotten to this 2 of 4 state where it's registered the things it can register without doing anything special. So it's made an entry in the Balena IoT backend and it's set up one end of the tunnel. The Kubernetes device and the ability to reserve it actually wait for this thing to come online and check in. And so what we would do next is download a disk image and flash a configuration file to that image and just drop it in here. The caveat being that I never quite got this working with the Wi-Fi here, so the live demo part of it isn't going, but I've got slides, so it's almost as good. Sorry, these slides were somewhere. Okay, so basically once it comes online for the first time, that health check will proceed because it will have self-enrolled in the cluster. And then once it's in the cluster and healthy, Blazor, the reservation service, sees it and goes, oh, this is fine to reserve. And if you set it as restricted to your project, it'll show up only as grayed out for everyone except the allowed projects. Otherwise, it'll show up for everyone. There we go. Yeah, and so we've got in our docs, we've got links to where to get each image download. It's specific per device because we're compiling against given kernel versions. So sometimes upgrading the base OS image will require us to update the builds for those kernel modules. And yes, and so once it's come online, you'll see this where it says steady for Kubernetes, it says steady under Blazor, and it will show up in this calendar where I will actually just pull up the calendar. So it's the same reservations tab as all the other Chameleon sites, and you just click device calendar instead of host calendar or flavor calendar. And we've got, okay, so I've got this reservation on one of the devices, I've got this reservation on a second device from the examples I just ran. I believe Rick has the big Orin, Jetson Orin reserved to do some testing on it. You'll see a lot of these are grayed out. These are because we default to showing everything that everyone's enrolled, but many of them are restricted, or many of them were like registered for a class and then kind of put aside. And so another thing on our roadmap, and something we're going to ask for sort of the user ergonomics of, is what is the life cycle of a device? And if you've registered it and then you left it alone for 6 months and it never came online, like should we delete that? Should we hide it? How do we make sure that that exists so you don't accidentally make 27 copies of it? And just generally, accessing this as much as possible. We tried to make this like the other sites. Everything else here, I've got kind of lists of best practices and ways to make the user experience easier. But it's not super interesting to kind of run through end to end. So it's just things like, don't bake all your state into the container because that's expensive and you can lose it. Build Docker images, get used to uploading, build locally, upload to Docker Hub, download it. If you have problems with the workflow or if this presents friction, let us know, because then we can prioritize putting more time into should we set up recipes for a Docker build VM? Or maybe do you need to use a beefier machine on Chameleon to do some expensive builds? Or is there a reason you can't use Docker Hub? Or this kind of constellation of potential limitations. Same thing as just following Docker best practices. To just downloading a 5 gig image onto a Pi is going to take forever, so don't do it if you can avoid it. Figure out how to make your runtime image small and do the development elsewhere. And this is related to what you were asking about, how do you add your own peripherals? The big task here is you plug it into the Pi and figure out, well, where does it show up under /dev? Right now, because we don't have an end-to-end dev mode to give you root on the Pi and Chia Edge, the best way to do this is plug it into stock Raspbian and be like, how would I use it if it was a normal Pi? And you just list oh, here's all the things under /dev it needs, and it needs to look up this thing under /sys to see I'm on a Pi 4, and it needs this library. And then submit a help desk ticket or put something on the forums being I'm trying to do X. And we can just, put in a mapping for, this will map everything up from /dev into the container, you can try it out. And we're in progress of adding some flags so you can, say you enrolled your own device, let's make it possible for you to, like, while flashing the image, drop an SSH key on there and just SSH into the host OS, but also flag it as, this device is in dev mode and no one else can use it. We have built the architecture with security in mind, so the device only has credentials and permissions to sort of update its own properties in the system. But there's the inherent risk of, this is a device physically in your possession, and if an end user runs some workload on there, there is no feasible way to stop you from examining their memory. So we just want to make it like, running workload on someone else's device is opt-in. And maybe don't put your one AWS token in there. Like, we don't think any of our users are actually malicious, but it's just like, come on guys, let's be professional about this. And have not shooting yourself in the foot defaults. So yeah, this is what we've got right now for the kind of common methods of interaction and best practices and some places where we really know we want to make the developer and user onboarding experience better. And that's easiest if people have cool ideas and we can work together to make it happen. So yeah, thank you. I'm happy to take questions. I'm happy to give Paul some time to set up. Many of you know where to find me already. But my email's on the staff page of the Chameleon website. Please feel free to reach out if you've got any questions or ideas.